Welcome back. In this segment, I want you to come up with a combinatorial proof of this theorem, which we discussed in the previous segment. So remember that to find a combinatorial proof, you must first identify a counting problem. And that problem must be solvable in two different ways. And these two ways of solving the problem will yield the two expressions in this equality. So remember, my advice when trying to find a combinatorial proof is always to start with the simplest looking expression, in this case, this one. So what is 3 to the power n? Well, it's 3 times 3 times 3 times 3 n times. And my hint here is to find a combinatorial problem where you're counting a number of strings of length n. So why don't you pause the video and come up with a combinatorial problem whose answer is obviously 3 to the power n. So let's consider a string of length n. So it has n positions. And if the total number of such strings is equal to 3 to the power n, then what can we infer about the possible number of letters at each position? Well, it must be equal to 3. So the particular counting problem we're going to look at then, it's a counting problem where the possible characters that can go at any position in the string is a set of 3 characters. Let's just call these characters A, B, and C. Doesn't really matter. So let's assume that we start with this counting problem. Before you go on, make sure you're convinced that the total number of strings of length n, where the strings are made up of characters from this set of characters or this alphabet, that number is indeed equal to 3 to the power n. Now, to complete the proof, you must find a second way of counting this total number of strings that will yield this expression here. So to get you started on that second approach, let's write down this expression, this summation formula, by expanding it to what it actually stands for. So it's going to be the sum for j equals 0 to n of this product. So when j is equal to 0, we're going to have n choose 0 times 2 power 0. And so on and so forth for j equals 1 all the way up to n minus 1 and then n. Well, to prove that this sum is equal to 3 to the power n, all you have to do now is to identify a way of counting these strings that breaks down into the corresponding cases here. So pause the video and come back when you have figured it out. So now let's look at these terms and see if we can identify what they're counting. Let's start with this one, since n choose n is equal to 1, so that disappears, and 2 to the power n is actually very similar to 3 to the power n. So how can we get 2 to the power n? Well, notice we could be counting the total number of strings of the same length n, but when we're only allowed to use 2 out of the 3 characters here. So let's say we eliminate one of the characters, say the A, from this alphabet, and now we're only allowed to use the B and the C, or in general, we're allowed to use 2 out of the 3 characters. Then 2 to the power n would be what? The total number of strings of length n that do not contain an A. So let's record that. Now that we've accounted for all of the strings of length n that do not contain any A's, the sum of all the other terms must be the total number of strings that contain at least one A. Now if we focus on the other end of the sum here, we have a term that's equal to 1. We have n choose 0 is equal to 1, 2 power 0 is also equal to 1. So when we multiply the two, we get a 1. So what's a special string among all the strings that contain at least one A? Well, it's the string that contains only A's. That is, there's only one such string because it's a string of n A's. So let's say that this term accounts for the strings that contain exactly n A's, and there's only one of those. Now let's focus our attention on this term. Since it contains a 2 to the power n minus 1, it seems like it will account for the set of strings of length n that can only take a B or C in n minus 1 of its positions. In other words, this looks like it could account for the total number of strings with a single A in them. So let's see how this works. If you were to build a string containing only one A, that means that string would have to contain n minus 1 other positions where you could place either a B or C. So the first step to build such a string would be to pick n minus 1 positions out of a total number of n positions, and then for each such position you would have a choice of a B or a C for the first chosen position, and then a B or a C for the second one, all the way up to the choice of a B or a C for the n minus first position. So you can multiply all of these possibilities, and that's how you get 2 to the power n minus 1. So again, this term accounts for the total number of strings that contain exactly one A. So now I hope you see maybe a pattern emerging here. Notice if you add up the number of A's in these strings, which is n, and the number of A's in those strings, which is 0, you get a total of n. So here we have a total of A's in each string of 1. So if we go on the other side, maybe this term accounts for the total number of strings that contain exactly n minus 1 A's, because n minus 1 plus 1 is also equal to n. So let's see how that would work. Let's say I want to build a string of length n that contain exactly n minus 1 A's. How would I do that? Well, notice in this string there's only a single position that does not contain an A. So to build such a string, you would first pick one position out of n to position the B or the C, and then you would have two options for each such position that you chose in the first step. So when you multiply these two numbers, then you get the number of strings that contain exactly n minus 1 A's. So notice, another way the pattern manifests itself is if you take the number here at the bottom and add it to the number of A's in the strings, you get n. 0 plus n is n. Similarly here, 1 plus n minus 1 is n. n minus 1 plus 1 is n, and n plus 0 is also n. So if we have a j here, this should be counting the total number of strings that contain exactly n minus j's. So let's make sure this works. How many strings of length n contain exactly n minus j's? Well, this is the same number as the number of strings of length n that contains exactly j positions in which you can put a B or a C. So to build such a string, you would first choose j positions out of n available positions, and for each one of these choices of positions, you would have 2 to the power j options to position either a B or a C in one of the j positions. So in conclusion then, the total number of strings of length n over this alphabet is definitely equal to the total number of strings of length n that do not contain any A's, plus the total number of strings of length n that contains exactly one A, plus plus the total number of strings of length n that contain exactly n minus j's, plus etc., the total number of strings of length n that contain exactly n minus 1 A's, plus, finally, the total number of strings of length n that contain exactly n A's. Since we've covered all of the possibilities and none of these sets of strings intersect, we have accounted for all of the possible strings of length n over this alphabet. And this is the conclusion of the combinatorial proof of this theorem.